Hello and welcome. Today we are going to start a new topic, very interesting topic and very important topic both for academics as well as practitioners, engineers. Uh, this is ADC and DAC. Okay, and you know possibly this that ADC stands for analog to digital converter, and DAC stands for digital to analog converter. Okay, so let me just recap quickly what do we mean by analog and what do we mean by digital. You may know it already, and we also discussed it briefly before while talking about digital voltmeters. Okay, so analog, let me do it this way. Analog, say we are talking about analog voltage, and we are talking about say digital voltage. So we are talking about voltage. Now say we have a voltage which lies between say in the range 0 to 7 volt. Say we have a voltage Vx such that 0 less than Vx less than 7 volt. Okay. So Vx, that means can be 0 volt, can be 0.1 volt, can be 0.2 volt, can be 3.4 volt, 3.437298 volt, anything between up to 7 volt, anything between 0 and 7 volt. And it can, I mean, if you express it in a decimal form, it can take many decimal places to represent it accurately. So that means this is a voltage which can take any value between these two ranges. Okay. So for example, so let's take an example. So think of a DC generator possibly. Okay, and you know that the output voltage, so this is the output voltage. You can change this voltage by say changing the strength of the magnetic field or by changing the speed of this generator, and you can say change the speed continuously, 300 rpm, 301 rpm, 400, anything. You can change the strength of the magnetic field, anything. So therefore, you can change the value of Vx continuously between 0 to 7 volt. But say now we want to store the value of this voltage in a computer. Okay. In a computer, we cannot store any number, any arbitrary number. Okay. For example, we may be not we possibly cannot store a number with this many decimal places if we are using say only 4 bits to store the number. Okay. So now if we want to store the value of Vx, this Vx, okay, say we measure Vx, we have measured the value of Vx, and that value we want to store in a computer. In computer, we cannot store in any arbitrary precision, infinite precision. But say we are storing it in say using say 3 bits. Okay, and with 3 bits, how many numbers can we represent? With 3 bits, we can represent the numbers, this number 0, 0, 0, 0, 0, 1, 0, 1, 0, so on up to 1, 1, 1. So this is same as in decimal 0, the decimal 1, decimal 2, and this is decimal 7. So these are the 8 numbers that we can represent using 3 bits. Now suppose we decide that okay, a value of 1 will represent 1 volt. Okay, so I may say okay, this value is equivalent to 0 volt, this value is equivalent to 1 volt, this value is equivalent to 2 volt, and this value is equivalent to 3 volt. Okay, so we have chosen the number 1 to represent 1 volt. Okay, so this way we can store, this is 7. So this way we can store 7 different values of the voltage. Okay, and now if we have Vx is equal to 3.3 volt measured, we cannot represent 3.3 using this previous scheme where we have 3 bits and we have chosen that each number should represent 1 volt. So we have to then approximate this Vx as maybe 3 volt, and we will store it as the binary number 0, 1, 1. This is equivalent to 3. Okay, so this is what is called the digital representation of a analog voltage. Analog voltage is something that can take any value. Digital means because we represent the value in digits, in numbers, so we cannot represent any arbitrary precision. So we can only represent discrete values of this voltage. Okay, so that is called the digital representation. Okay, it's a discrete representation of this Vx. Okay, so this is digital equivalent of Vx, which is equal to 3.3 volt. So it's a discrete representation. This is what you probably know already. Now, so we will talk about in this chapter we will talk about two devices, two instruments. One is an ADC, another is a DAC. What is ADC? Analog to digital converter, right? So this will take, so if I draw it as a black box, ADC, so it will take a voltage Vi analog, it can take any value and it will give digital output. So, digital output means this number will be represented in the form of bits. Okay. So, each bit I draw as a output. So, this is a 3-bit output, and if this is 3.3 volt, okay, in this scheme, so it should come out as 0, 1 and 1, okay, where this is the LSB, this one the rightmost bit, and this is the MSB, this is the leftmost bit. Okay. So, this is what an ADC does. Now, let me ask a question, a stupid question, wrong question. A stupid question. Say input to an ADC is equal to 3.3 volt. Okay. What is the output? This is a question. Do you know the answer? There is no answer, because this is a stupid question. Okay, so I cannot give any answer unless I know more information about this ADC. Okay, so answer not possible if I do not know the number of bits, number of output bits of this ADC. Okay. So, without this, this question is meaningless. Okay, say now I say, okay, fine, let's take 3-bit ADC, which means the number of output bits, number of output lines are 3. So, can I now say what is the output if the input is 3.3 volt? Can I ask this question? No. This is still a stupid question, still a wrong question, because I cannot give you what the output value is unless I know the resolution or how much is the number 001 is equivalent to in terms of volt. Okay. So, we also need to know this is 3-bit. So, okay, this is the first number, this is equal to how much volt. If we do not know this value, we cannot give you the answer. Okay. So, now if I say, okay, let us take 001 should represent 1 volt. Okay, now I can tell you the answer. Okay, so now the answer will be, we know that input is 3.3 volt and the number 1, okay, this number 1 is equal to 1 volt. So, now if I divide 3.3 divided by 1 volt, this is, and then if I round it off, say for example, Okay, let me write it this way. 3.3 volt divided by 1 volt. This is approximately equal to 3. So this is equal to 0, 1, 1. Okay, so this will be the output. So therefore, I need to know essentially this answer. How much this number is equivalent to in terms of the voltage. Otherwise, it's meaningless. Okay, so I may sometimes tell you that, okay, let's take this 001 is equivalent to say 2 volt. Okay, if that is the case, then the output, now the output will change, definitely a change. Then output will become, so 3.3 divided by 2 volt. So this is how much? This is I think 1.65, I guess. If it is wrong, please correct me. So, and which is approximately equal to 2 volt. This is closer to 2 volt than 1 volt. So I may then say, okay, this will be equivalent to 0, 1, 0 in binary. This is 2. Sorry, not volt. Okay, this is 2. So then this will be the answer. So if I just change this, the answer changes, and this is called the resolution. Okay, so resolution of an ADC. So this is the voltage represented by this number, by the binary number 1, 0, 0, depending on as many bits as we have, those many zeros. Okay, if we have n bits, then n minus 1, 0, and then 1. Okay, so the task of an ADC is to take an analog voltage and convert it into a digital value. Okay, so all these outputs can either be high or low. Okay, these cannot take any arbitrary value. This cannot take any value like 2.5 volt, 2.6 volt. It can take only logical 0 and logical 1 volt, whatever is represented by logical 0 and logical 1. Okay, and so I will put another arrow and I will call this input as V resolution. This is what tells us the number 001 is equivalent to how much. If I call the V resolution is 1 volt, okay, then this is 3. 3 means input should be approximately 3 volt. Okay. So this is about ADC. So very importantly, you just note these facts. Number one, it takes an analog input, it gives a digital output, and what will be the output that definitely is controlled, is defined by this V resolution of this. Okay. Now what is a DAC? DAC on the other hand is the opposite thing. Okay. So DAC will take, we already have talked about it, so very quickly. So it will take digital inputs So this can take only logical high or low value. It cannot take any arbitrary value between high and low. But this is analog output. So this voltage VO can take any arbitrary value. Okay. Now let me ask you once again. Let's see how much we have understood. Say the input is 0, 1, 0. Or say the input is let's take okay, this is 0, 1, 0. I also have to say which is LSB, which is MSB here. Okay, otherwise it's meaningless. So let me say this is MSB, this is LSB, although this is symmetric. Okay. So say this is the input. So I will ask output is equal to how much? Can you say? No, because I also have to say this V resolution is equal to how much? This is important. Okay. So therefore, I will again put another extra input V resolution, just like an ADC. Now, if I say this is equal to say let us take 1.5 volt for example, then VO will be how much? Now it is very simple. This will be V resolution multiplied by this number 010. Now this is 1.5 volt and this is what? This is binary 2 into 2. So output will be 3 volt. This is the answer. Okay. So this is what DAC is supposed to do, just opposite to an ADC. Okay. Now, so once we know what ADC and what a DAC is, next thing which is important is to see some circuit of ADC and DAC. So say circuits of ADC. Okay. Do we not, have we not already studied this in this course in the previous week? Yes. So you recall, the digital voltmeters that we have studied, digital voltmeters that we have studied. Let me just name them: linear ramp type, then we have studied what digital ramp type, successive approximation type, I am saying that all these voltmeters are also ADCs. Okay. They also act as an ADC. We do not have to study anything new. If you have understood those classes, then you do not have to study anything new, or you can go back and understand those circuits. Okay. Because these voltmeters are essentially ADCs. Why? Because essentially what we have a this comparator which takes two inputs Vi. So this is unknown input, and here ramp voltage. It can be linear ramp, it can be digital ramp. In case of successive approximation type, okay, this will not be ramp in that for this one. So let me not write ramp, let me just call it a voltage to compare, and then this drives a counter okay. So the moment when we find that these two voltages are comparable, if this, maybe this is increasing and at some point these two become comparable, at that time the counter stops, okay, and the value of the counter at that moment will represent the digital equivalent of this input voltage. That is what I am saying. Let me write after the comparison is over, the value of the counter will represent the digital equivalent of Vi input. Okay. For our better understanding, let me just consider this one. Okay, digital ramp type. Okay. So let me just talk about one of them. Others will be very much similar, which you can think yourself. Okay. So let's think about a digital ramp type voltmeter. Okay. So what do we have from this counter? We have a DAC. We haven't seen the circuit of a DAC yet. We shall see that soon, but we know what it does. It just takes this outputs from the counter 1, 2, 3, 4, 5, 6, 7, 8 maybe, and it converts it into a voltage to be compared. Okay. So this is a digital linear ramp type voltmeter, not successive approximation. So if the say if the okay, so this will also have this input V resolution, such that if this is a number NB, this voltage here Vy is equal to NB times V resolution. Okay. So say if Vi, let's take an example. Say if Vi is equal to 5.5 times V resolution, right, then when this measurement is starting, all the counter values are initially 0. So initially counter is equal to 0, 0, 0, 0, 0, 0, 0, 0, and Vy is therefore is also equal to 0 volt. Okay. Then counter increases and Vy, this one also increases. Okay. So counter value becomes say 0, 0, I mean so many zeros and 1, then Vy becomes V resolution, then the counter becomes 0, 0, 0, 0, 1, 0, then it becomes 2 V resolution. Okay. And each time we are asking this question, is Vi greater than V resolution? Okay. For the value of 5.5, the answer is yes. Here also we ask, is Vi greater than 2 V resolution? The answer is yes. And this way we will continue up to a point which will be equal to 5, means 101. So, Vy will be this is the counter value, this is the Vy value, this will be 5 times V resolution. Same question, the answer will be again yes. Next time it will be 0, 1, no, 0, 0, 1, 1, 0. This is 6. We will ask, the comparator will ask, resolution. The answer is no. This time the answer is no. So, the counter stops with a value zero, so many zeros, and then 1, 1, 0, which is same as 6. Okay. So, the counter stops with a value of 6. So, this implies, okay, so this actually implies, so this implies that Vi is approximately equal to 6 V resolution. Okay. We cannot represent fractions, so therefore, it gets converted to integer. So, we will say that Vi is approximately 6 V resolution. So, therefore, we can also say that okay, the digital equivalent of the input Vi is equal to 6, which is same as some zeros and then 1, 1, 0. Okay. So, this is the digital equivalent of the with, okay, I should also write with V resolution TION is equal to something, whatever is the value that we apply here. Okay, I should also say that value, then it becomes more meaningful. Okay. So, now for a chosen value of V resolution, therefore, the last value, final value of the counter will tell me the digital equivalent of this input voltage. So, this is therefore is also an ADC. So, let me write, this is also an ADC, digital ramp type ADC. Okay. Similarly, the successive approximation type voltmeter that we have studied can also be used as a successive approximation type ADC. Okay. So, therefore, we need not study ADC separately from voltmeters. Voltmeters are ADC, digital voltmeter, any digital voltmeter is ADC, no problem. I mean, okay. So, that is about ADC circuits. Now, in the Next we will see some DAC circuits. Okay. This is going to be something new. So please watch this with patience and with care. So we shall see a few DAC circuits depending on time. So please get refreshed at this point, refresh your mind, and let's start it again. This is a new topic. Okay. Say we have a set of resistances which are connected like this. I will start my drawing from the right side. Call this is equal to R, this is also equal to R. And so these two together are in series 2R. So there, since this is 2R, I will connect another 2R resistance in parallel. This is 2R. So this is R, 2R, and this is 2R. So R plus R is 2R. I have connected another 2R, and looking between these 2 points, I mean this and the ground. Okay. If you want, you can think these are connected. So now between these 2 points, the total resistance is how much? 2R parallel 2R. 2R parallel 2R is R. Okay, same resistance. So they are in parallel, it will get halved. Half of 2R is R. So between these 2 points, it is R. Let me erase it because I need some space later there. So this is between ground and this point, the resistance is how much? As seen from here, it is R. Now what I will do, I will add another R to this. So this plus another R. Now this and this entire thing, you can think they are in series. So think between between these 2 points. So between the ground and this point, what is the resistance? Between the ground and this point, this is R and another R in series. R plus R is 2R. Now what I will do is this. I will connect with this another 2R. Okay. So I add R in series to make it 2R, and then I add 2R in parallel to make it halved again R. So if you see between these 2 points, ground and this point, total resistance is how much? See, this is R plus R, so that means this part is 2R parallel 2R. 2R parallel 2R is R. So between these 2 points is, therefore the resistance is R between these 2 points. Okay. So now what I will do, you possibly have understood my trick. I will add another R in series. So now from here to ground, this is 2R, and once it becomes 2R, I will add a 2R in parallel. Okay. So now between these 2 points, here and here, here and here, the resistance is R. Okay. 1, 2, 3. Okay, let me take one more. Okay. So what is the resistance between these 2 points. If you measure with a ohm meter, what is the resistance will you get? This is equal to R. Total resistance between these 2 points is R. Okay. Let me write that also symbolically with a different color, a light color. So the total resistance between these 2 points is between ground and this point is R. Okay. Now what I will do here, I will connect a voltage source. This side is grounded. Grounded means this is all grounds are connected. You can think in that way. Call this voltage as V ref, some reference voltage. Okay, plus minus. So how much current will flow? Call this current as I ref. How much will this be? This will be this voltage divided by this resistance, which is the equivalent resistance of all these things, okay, which is R. So this will be V ref divided by R. So this is the current that flows, right? Now, so this much current will come here, V ref by R, which is I ref, and here it will get divided into 2 halves. One will go like this, another will go like this. How much will go towards the right and how much will go towards the left? That depends on this resistance and the total equivalent resistance between, say, these 2 points. So total equivalent resistance between these 2 points, if you calculate, it will be 2R. That's how we did it. Now, let me just do it once again. You see, between this point and ground, as seen from the left, if you see from the left side, okay, then between this point and the ground, the total resistance is 2R, R plus R2R. Similarly, then between this point and this point, it will be 2R parallel, 2R is R. Again, as seen from the left side, okay, as seen from this side, okay, so this side, see according in the direction of my finger, okay. No, sorry, lifts, okay, see in, sorry, because the screen is mirrored, see in this direction, right. So look from in the direction of my finger. If you are looking from here, the total resistance between these 2 points is R. Similarly, between this point and ground, this R plus this R, it will be 2R. Okay, so on. So this will be 2R. You just do it yourself. I know the answer, so I am doing it quickly. So this will also be 2R. Okay. So you see, whatever current comes here, it will get divided into 2 halves, 1 and 2. This resistance, this total equivalent resistance here is 2R. This is also 2R. So that means the current will get divided into equal halves. Half will go towards the right. So this current will therefore I ref by 2, and this current will also be I ref by 2. Similarly, this current comes here, and at this point it will get divided into 2 halves, 1 and 2. You see, this resistance is 2R and the equivalent resistance is again 2R. So half of this current will go towards the right. So that is I ref by 4, and half of it will come this way. So that will be I ref by 4. Okay, and in this way, if you just continue the analysis, you will see this current will again be half of this. So this will be I ref by 8. This will be I ref by 8. Similarly, this will be I ref. This is I ref by 16, and this current will be I ref by 16. Let me write it. Let me erase one of this. Okay. I'll need some space. This is I ref by 16. Okay. So this is how the current distribution will be. Now, the next thing that I will do is this. Instead of connecting this to grounds, if I keep a switch here, which can be connected to either ground or something else. So all this you can either connect it to ground or you can connect it to something else, which I haven't drawn yet. Here also, here also. If these are connected to ground, then definitely this will be the current distribution as we have discussed. But if we connect it to here, one of them or many of them, then the current distribution may not be like this, because we have calculated this assuming these are connected to ground. But okay, I will ensure that these are, okay, let me just connect this all, and I am ensuring you that this potential is 0 volt. Even if it is not physically the ground or earth or physically 0 potential point, I am ensuring the potential here will be 0 or very close to 0. Okay? If I ensure you that, then that means no matter whether you connect it here or you connect it here, the current distribution in this resistance will remain same, because both of them have same potential. Okay? So I will ensure that this is 0 volt. How? Later. Okay, the last one will be connected to the ground directly. This is connected to the ground directly. These are switchable. Okay, so this I have to ensure that this is 0. I have to ensure 0 volt. Now you see what I do. I will take an inverting amplifier with op amp. Minus plus, negative feedback, call this resistance RF, because this is the feedback resistance, this is the output. This I will connect it to the ground. And now what I will do, this is quite interesting, I will connect this to here, right? Now you see, if the virtual sorting is true in this circuit, if the virtual sorting is true, then since this is 0 volt, this will also be 0 volt. I wanted to ensure this as 0 volt, and this will be ensured by the virtual sorting property of this circuit. How? Let me just tell you very quickly that, okay, this is a positive potential. So this side you see there is a positive voltage, and this will try to increase the voltage at this point. This will try to increase the voltage at this point because there is only a positive supply voltage, and okay, also this is connected to 0. So everything here must lie therefore between 0 volt and this VDEF. There is no negative potential at all. So all the potentials in this part of the circuit will definitely be between 0 and VDEF, positive. So this circuit will therefore try to increase the potential at this point to some positive value. And if it is increased to some positive value, then you know the op amp, the output of the op amp will try to go down. Why? Because Vn is going to be positive more than Vp, so the output will go down, and which will, because of this feedback, will decrease the potential at this point. So this circuit will try to increase the potential at this point, and this output will, by virtue of negative feedback, will decrease the potential at this point, and therefore at the equilibrium this potential will also be equal to 0 volt, and this is by virtue of virtual sorting, which is applicable in this circuit. So this is ensured by virtue of virtual sorting applicable in this circuit. Okay. So right now, so that means this will be definitely 0 volt, this is 0 volt, this is 0, this is 0, these are also 0. Now I can connect this switch to here or to here. No matter I connect it here or here, the potential here is 0. So that means this current will remain same as Iref by 2, no matter it is connected to here or here. The only difference will be is that if I connect it here, then this current will go directly to the ground, and if I connect it to here, then this current will go like this to the op amp. Okay, so then this current will come like this to the op amp, but it cannot go into the op amp, so it will go through the RF, this resistance, and will come like this, and then will go to ground through the op amp's output. Okay, so this current will go either like this or will go to the ground directly. Okay, now I have this, let me call these switches as D, let me start from this side, D0, D1, D2 and D3. These are switches, and they can be connected to this op amp or to the ground. And I say that D0, I will say that this is, with this symbol, if I write D0 equal to 0, means switch D0 is connected to ground directly. This is what I will mean when if I say D0 is equal to D0, and if I say D0 equal to 1, this means the switch D0 is connected to the op amp. Okay, so I can also say D0 equal to low, which will mean the switch is connected to the ground, and if I say D0 is high, digital high, logic high or 1, that means this switch is connected to the op amp here. Similarly for D1, D2, D3, etc. Okay, so I can say D3 is equal to 0, which means this is connected to the ground. If I say D3 equal to 1, this is connected to the op amp. Okay, And these switches in an actual circuit are not manual switches, although I have drawn manual switches. These are in an actual circuit, they can be electronic switches. So this can be electronic switches like transistor, electronically controllable switches, switches, okay. And I call them 0 or 1 to mean whether they are connected to ground or to the op amp. Okay. Okay. So now the next thing we will do is we will calculate this voltage, VO, this output voltage. Okay. How to calculate this voltage? This point we know it is at 0 volt. So how much will be VO? VO will be, if this current is I, right, then VO will be, so this is 0 volt, 0 volt minus this drop which is IRF, that will give VO. So VO I can write, this is 0 minus IRF, right. So this is the output voltage. And okay, so this is minus IRF, and so I have to find the value of I. Okay, and now what is I? Let me write it here. I, this current is will be same as this current if this switch is connected to the op amp. Okay, so and this current is how much? IRF by 2. If this switch is connected to the op amp here, then this current IRF by 2 will come like this. So I can write this is equal to IRF by 2 multiplied by D3. Now if D3 is equal to 1, you see, if this is equal to 1, then that means this is connected to this, so this current comes like this. And if D3 is equal to 0, then no current can come like this, but this is 0 means 0 times something, this will become 0. Okay, you see that? So just a short note, if D3 is equal to 0, then IRF by 2 into D3, this is also equal to 0, and also no current comes to the op amp, as the current is going to the ground directly. So this current here, will go to the ground directly, so this will not come. Okay, so this is the nice, this is how mathematically nice it is to represent this with D0 is equal to means switch is connected to ground, and D1 means the current goes to the op amp. So this is due to this current. Now this current can also come to the op amp or may not come. So if it comes to the op amp, then I also have to add this value. So this will be IRef by 4 multiplied by whether this actually comes here or it goes directly to the ground, which means D2. Similarly, this current I may have to add or may not. So I write IRef by 8 multiplied by D1. Similarly, this current I may have to add or may not by 16 multiplied by D0. So this is I, and if this is I, then I can write V. Now I don't need to look at the circuit, I will work with the equations only. So now VO I can write is equal to minus I times RF or minus RF times I, and I is this. And how much is IREF? Okay, that you see here, we already have computed. IREF is VREF by R in this circuit. So this, therefore I can write IREF is VREF by R, or let me take this IREF outside, common. And now I write this as VREF by R multiplied by D3 So you see the output voltage VO is governed by this, and you can think that okay, these are the digital inputs. So D3, D2, D1, D0, they can take values 0 or 1, logical 0 or logical high or low. Okay? And depending on these values, the output will change. So take cases. So for example, you take D3, D2, D1, D0 versus VO. So you take all these are 0, means all these switches are connected to the ground directly, then the output will be how much? It will be 0. Okay? And if I take this equal to 0, 0, 0, 1, then the output will be, so this is 0, 0, 0, 1. So then I will have 1 by 16 only. So that we'll have RF minus RF to be precise, VREF by R into 1 by 16. Okay. Similarly, you can take 0, 0, 1, 0. This will be minus RF by R VREF into 1 by 8. This is only there. So you see, VO is actually equal to this value okay, multiplied by a number, a binary number represented by the switch. Okay. I may also write it this way. It will take divide by 16. Okay, just watch this. So this is this. So I write it this way, multiplied by 1. I can do it, right? Now this 1 by 8, I will write this as 1 by 16 into 2. Okay. Similarly, the next one. So I mean, I can write them in all this way. So for this, you will see this is equal to, the output will be, if you compute from this, it will be RF VREF by R by 16 into 3. So I can write this, I take the 16 here and a binary number represented by the switches. Okay. So I call this as my V resolution times binary number. So this is what how it looks like for a digital to analog digital to analog converter DAC. Output is some resolution times this, some resolution voltage times a binary number. So this acts as a digital to analog converter. Thank you.